lecture. I will share the screen. Okay, this is what we will discuss today. It's about the thermodynamics, chemical thermodynamics. Actually, this is just a review what you have received in the last semester. Last semester you had a thermodynamic class, is it correct? Chemical engineering thermodynamic. Yeah, and one of its chapter, it discussed about the thermodynamic reaction equilibrium. Gitu ya. It's actually usually it's final parts for the thermodynamic, for the chemical engineering thermodynamics, and I believe the lecturer is Pak Hardev.
Yes, sir.
Yeah, I believe Pak Hardev has already discussed a lot about the reaction thermodynamics, reaction equilibrium. So in this chapter, I will just review what Pak Hardev already taught to you. Yeah. Okay. Chemical thermodynamics. Okay. Yeah, our lecture now is chemical reaction engineering, which is focused more about the kinetics. Yeah, Pak Yogi, I think Pak Yogi last week has already mentioned that the focus on the chemical reaction engineering is about the kinetics, gitu ya, about the reaction kinetics. But why we still need to learn about thermodynamics? Gitu? Because thermodynamic become a basic for all reaction. Gitu. When we find a reaction, when we find a reaction and we want to evaluate whether the reaction could happen or not, it can be evaluated firstly by thermodynamic. Gitu ya. So the thermodynamic is the early evaluation for every single reaction. Gitu. Okay. Yeah, thermodynamic, like you've learned last semester, it talks about mostly about the energy. And you know that every chemical reaction involves energy. Gitu ya? Either exothermic or endothermic. Gitu ya? Every chemical reaction involves energy. That's why we can evaluate the reaction firstly by thermodynamic. Gitu. Jadi yeah, it's the early evaluation. Gitu. What can we evaluate from the thermodynamic of reaction? We can evaluate the maximum conversion. We evaluate maximum conversion by using thermodynamic. From this thermodynamic, from this maximum conversion, or we call it equilibrium conversion, we can determine whether a single reaction is appropriate to be done or not. Yeah. For example, maybe about 15 years ago, do you know we have a chemical reaction engineering laboratory? in chemical engineering program? Yeah, chemical engineering, chemical reaction engineering laboratory, or lab TRK. Maybe you've heard, maybe recently you heard it a lot because our lab, or we call it TRK gitu ya, teknik reaksi kimia, we develop so many catalysts for so many process. Like we developed the catalyst to produce the gasoline from palm oil. We also developed the catalyst for diesel oil from the palm oil, gitu ya. Yeah, we we developed a lot of kind of catalyst. One of catalyst we developed is, we call it the sponge iron. We call it the sponge iron. Pak Bagio and Bu Melia developed it maybe about 15 years ago when I still in the college, like you gitu ya. The catalyst actually is so simple. It's just iron oxide. Iron oxide, Fa2O3. This is iron oxide. This catalyst is used to absorb the sulfur from the natural gas. To absorb sulfur from the natural gas, so the gas will be sulfur free, because when we use the natural gas, it must be sulfur free. Yeah. So the sulfur is absorbed to the catalyst, so we called it as a sponge iron. Okay, so how to make it? How to make this catalyst? How to make this catalyst? Do you know what is this iron oxide is? I think you've seen it a lot in your life. I believe you've seen it a lot in your life. Ada yang tahu? Iron oxide or oxidized iron. What is it called in the daily terminology?
Is it ruster?
Pardon?
Rust?
Yes, it's a rust. Actually, it's a rust. Ya, saya yakin kalian pasti udah sering kan lihat karat ya. That rustic iron gitu ya. Actually, it's a rust. So it occurs naturally. Itu kan ya? I think you see it everywhere when you see a bare iron gitu ya. The iron without being painted, it will be rusted fast enough gitu ya. So you will see so many rust. So it occurs natural. It occurs naturally. So making iron oxide actually is not that difficult gitu. Karena prosesnya natural. When you put iron on just put iron in the open air, it will be rusted. Gitu ya. So in this condition, we can say that the production of iron oxide from Fe plus O2 to form Fe2O3 is thermodynamically viable, thermodynamically feasible. Gitu ya. It's to make an iron oxide from the iron metal is thermodynamically feasible. Karena itu terjadi secara natural. It happens naturally. Gitu. Gitu. But the question is how to make it efficiently. Gitu ya. The metal oxidation is a very slow process. Like the rust formation is a slow process. Gitu ya. Kalau kalian lihat ya kan besi berkarat, apakah langsung tiba-tiba blok jadi what's the color of rust?
Bronze chocolate gitu, sir.
Like a brownish, like a brownish chocolate, like a gitu ya, yellowish brownish gitu ya. So when you have like let's say an iron bar, you put it outside in the open air, will it become rusted fast, so fast? Jadi tiba-tiba ketika kamu, if you have an iron bar, you put it in open air, tiba-tiba semuanya jadi kuningan gitu. It will suddenly become yellowish, and all parts are rusted. Secepat itu nggak?
No, sir.
No, it's a slow process. Yeah, pelan-pelan. It's a slow process. So when we make an iron oxide as a catalyst, can we do it that way? Just put our catalyst, just put our iron metal, our iron catalyst in the open air, and then just let it rust naturally? Enggak kan ya? Kalau kita biar if we let it happen naturally, it will take a lot of time gitu. So we need to speed up the process. We need to speed up the process. Nah, that's what we learn in the chemical reaction engineering 1 gitu. How to make a process faster. How to evaluate the kinetic, how to evaluate a reaction, how to evaluate the reaction in the term of its speed gitu ya. But first, what we will need to evaluate is the thermodynamic. Is it thermodynamically feasible or not? If it is feasible thermodynamically, we can do some kinds of technique to make it happen faster, like this iron oxide production. In this iron oxide production, we see that thermodynamically, this process is very feasible. Iron can be oxidized naturally. It means that thermodynamically, this process is feasible. Gitu ya. Kalau suatu proses atau suatu reaksi, is it okay if I use the mixed language? Sorry ya, my English is not so good, so sometimes I need to use bahasa Indonesia to make a clear explanation, gitu ya. Kalau suatu proses itu bisa berlangsung secara natural, itu berarti prosesnya thermodynamically feasible. Gitu. That's a key point. If a process can happen naturally in the nature, it means that the process is thermodynamically visible. Itu kuncinya. Jadi kalau menemukan suatu proses yang di alam ini bisa terjadi, it means that it must be visible thermodynamically. Gitu. Nah, cuman the question is how to make it technologically and economically visible. Gitu. Because we are, as a chemical engineers, we have to see the process. We have to see the process in the bigger vision, gitu ya, in the commercial point of view. Gitu. Kalau dosen-dosen saya dulu bilangnya teknik kimia itu UUD, ujung-ujungnya duit. Gitu. Karena in the chemical engineering, we see the process for a bigger scale, for the economic scale. Beda sama teman-teman kita di kimia. Kalau di kimia melihat suatu proses, melihat suatu reaksi, okay, it can be happening naturally. It can be happening. Like misalnya kalau kita menemukan suatu barang, kita menemukan suatu benda, menemukan suatu compound, gitu, menemukan suatu chemicals, for the chemist, their focus is just how to make that things, gitu ya. Untuk seorang ahli kimia, membuat suatu compound, membuat suatu senyawa kimia, it's just a matter of how is it possible to make it. Mungkin nggak bisa dibuat, but we as a chemical engineers, we have to see that can we make this compound economically, gitu ya. Bisa nggak kita bikin senyawa ini secara ekonomis, gitu. Karena nanti ujung-ujungnya kita harus jualan, gitu. Nah, jadi batasan the boundaries, whether the reaction can happen or not is thermodynamic. Gitu, itu batasan pertamanya. Okay, thermodynamic behavior of a reaction is quantified by this Gibbs free energy and enthalpy. These two thermodynamic terms will be used to evaluate a reaction. Gitu ya. How to use it, we will see it later. Gitu. Okay. Gibbs free energy, energi bebas Gibbs, the Gibbs free energy. I will not explain about the philosophical definition because I think Pak Hardev has already mentioned it when he thought about the second law of thermodynamics, gitu ya. So here I will just explain what is the function of Gibbs free energy to evaluate a reaction. Okay, so Gibbs free energy explain about the behavior of the reaction equilibrium. Okay, what kind of behavior? What kind of behavior? First, about the reversibility of the reaction, whether it can be done reversibly or just in one way. Okay, and another, Gibbs free energy can also be used to evaluate the maximum conversion. Conversion. Maybe Pak Hardev already mentioned about this formula. gitu ya. Delta G equals to minus RT ln K. Gitu. From this formula, we can evaluate the equilibrium condition. This is the equilibrium constant. Equilibrium constant by evaluating the Gibbs free energy. Gitu ya. So we can evaluate the equilibrium constant. We can evaluate the equilibrium condition when we know the Gibbs free energy of the reaction by using this formula. Okay. Okay, if you have question, you can ask anytime, yeah. If you feel that my explanation is not clear enough, you can ask for more explanation, yeah. Okay, you can ask anytime. Okay, for this reaction behavior, this is the rule of thumb, but it's not that strict actually, but it's just the apa ya istilahnya, panduan cepat lah. It's just a brief, it's a brief and fast guidance, gitu, early guidance about the feasibility of the reaction, gitu ya. If we have a delta G of reaction less than 10 kilocalorie per mole, we can say it clearly that the reaction is very proper. It is feasible to be done, gitu ya. If the delta G is if the delta G is less than minus 10 kilocalorie per mole, we can say that the reaction is thermodynamically feasible. Very, very feasible. Very feasible. Okay. Then if the delta G is in between minus 10 to 0, yeah, we can call it, yeah, it's quite feasible. It's still feasible. It's still feasible, gitu ya. If the delta G is positive, but it's still less than plus 10, it means that this reaction needs some more effort to be properly done, gitu ya. Jadi kalau delta G-nya positif tapi ya positif sedikit, ya we need little extra effort to make it happen, gitu. Tetapi kalau sudah delta G-nya sudah sangat besar, delta G more than plus 10 kilocalorie per mole, usually people will leave it. We will find another route to make it. If the delta G is more than plus 10 kilocalorie per mole, we need to find another route to make that happen. Gitu. Guidance seperti itu. Lalu, where this number comes from? Kira-kira munculnya dari mana? Where these numbers come from? It comes from this formula. Let's see. Let's say if the delta G, let's say, is very negative. We put to this formula if the delta G is negative, can R be negative? Can the temperature be negative? No, right? R should be positive. Temperature should be positive as well. Okay, so if the delta G is negative, how about these? How about this ln K? Is it positive or negative?
Negative, sir.
We have negative here from the formula.
Also, it's positive.
So the K must be positive, kan? So the equilibrium constant must be ln K. Ln K must be positive. Ln K must be positive. What does it mean? What does it mean? If ln K is positive, it means that the K is higher than 1 or lower than 1?
Higher than 1.
Lebih dari 1 ya. Kan sifat dari logaritma seperti itu ya. Kalau ln-nya negatif, berarti dia less than 1 kan? If the ln K is negative, means that the K is less than 1 or between 0 and 1. Between 0 and 1. But if the ln K is positive, means that the K is higher than 1. And what is K? Konsentrasi timbangan itu apa? What is the equilibrium constant? Gampangnya apa? Gampangnya apa? Mungkin in your high school or in your TPB, you learn about the equilibrium constant. Gampangnya aja. The K equals to mole of the product, gitu kan ya? Divided by mole of the remaining reactant, gitu kan ya? Betul ya? Ya pangkat-pangkatnya oke lah. For the pangkat-pangkatnya nanti kita lihat sesuai dengan reaksi stoichiometric reaction. But the point is the equilibrium constant is the comparison between the mole of the product with the mole of the reactant. Kalau lebih dari 1, artinya apa? If the equilibrium constant more than 1, it means that kalau K-nya lebih dari 1, berarti kira-kira apa? Berarti kira-kira mole of the product is larger or smaller than the mole of the reactant?
Larger, sir.
Larger. If the K is more than 1, so it means that the mole of the product will be higher or will be larger than the mole of the reactant. Gitu. Produknya lebih banyak daripada reaktannya. Gitu. Artinya apa? Artinya the products are converted, the reactant are converted to produce the product. That's the logic. Logikanya seperti itu ya. That's the logic. If the K is higher than 1, it means that the mole of the product is higher than the mole of the remaining reactant. So it means that most of the reactants are converted to produce the product. Artinya reaksinya berjalan sehingga reaktannya bisa berubah menjadi produk. Gitu. So if you take a look back gitu ya, ini terjadi ketika it happens when the delta G is negative. Gitu. Jadi kalau delta G-nya, if the delta G is negative, means that the K is delta G negative means that the ln K is positive, so that the K is more than 1. It means that the mole of the product is higher than the mole of reactant. It means that the reaction happens. Gitu. Oke, kebayang? Oke ya. Oke. So if the delta G is positive, you can do the same thing, gitu ya. If the delta G is positive, then the ln K is negative, means that the K is lower than 1. It means that the product is less than the reactant. So the reaction is not happen effectively. Gitu. Gitu ya kira-kira. Yeah, this equilibrium constant come from the reversible reaction, gitu ya. For example, this is the dehydration reaction of butanol to form dibutyl ether. But at the same time, butanol can also be dehydrated to form a butane, gitu ya. So it's the parallel reaction. So from the thermodynamic reaction, we can, let's say our product is this. We want to produce dibutyl ether. So from the thermodynamic reaction, we need to find a suitable condition. As such, more butanol converted to produce dibutyl ether compared with butane. Gitu. How to evaluate it? We can evaluate it by the thermodynamic data. Gitu. Nah, this is the data. Gitu ya, the data of delta G reaction as a function of temperature. Gitu ya. Which one is our product? Let's say we want our desired product is this. Gitu ya. From the thermodynamic evaluation, we can evaluate at what condition, at what temperature the reaction should be done in order to get more dibutyl ether than the others. It's just the example. Gitu. Jadi kita bisa memanfaatkan thermodynamic evaluation to determine the condition of the reaction. Gitu ya, misalkan seperti itu. Nah, this is the detail of the reaction equilibrium constant. I believe that you get it from Pak Hardev, gitu ya. Betul ya? You still remember this equation? I asked about whether you still remember, not you still understand. Saya cuma bertanya, masih ingat enggak? Masih ingat atau enggak? Bukan masih paham atau enggak? Gitu. Gitu. Ya kan ya, Pak Hardev sempat masuk sampai sini kan ya? Betul?
Not sure, sir.
Not sure.
Sir, I can remember.
Okay, I think yeah, okay, I will just I will just remind a little gitu ya. Actually you already get it from high school as well actually. Gitu. Hanya mungkin notasinya tidak dibuat sepusing ini gitu ya. So actually this capital pi quite similar with this sigma. Has a similar function. Bedanya apa? What is sigma? What is the function of sigma?
Is the total sum, sir?
Summarize A plus B plus C gitu ya. Now this capital pi has a similar function, but not subtraction, but multiplication. So if we have E, it means 1, 2, 3 times 1 times 2 times 3 times 4, and etc. and so on. Gitu. So it means that this equilibrium constant is A1 powered by its stoichiometric coefficient multiplied by compound 2 multiplied by its stoichiometric coefficient, compound 3 powered by this its stoichiometric coefficient, and so on. And here we have an agreement. We have an agreement here that the coefficient, the stoichiometric coefficient, will be positive for apa? Coefficient stoichiometric itu positif untuk
Products.
produk. Gitu ya. Sedangkan while the coefficient will be negative for reactant. Gitu ya. So if we have this reaction, the component A, component B, the coefficient will be, it has coefficient of B, gitu kan ya? So that it will be B powered by minus B, karena because B in this reaction is a reactant. It's a reactant, right? So the coefficient is negative, gitu ya. C is the same, gitu ya. C juga reactant, so that the coefficient is negative. While S and T, they are a product, so that the coefficient is positive. Jadi kalau disusun ulang, jadinya kira-kira seperti ini. It's the same with what you've learned from the high school. Gitu ya, di SMA juga kan kalian you've learned that the equilibrium constant is a concentration of the product powered by its coefficient divided by the concentration of reaction, the concentration of reactant powered by its stoichiometric coefficient. Itu kan ya, dia sama berarti seperti itu kan ya? Dia sama berarti seperti itu kan ya? You've learned that from the high school, so you can, if you feel so confused with this notation, just remind aja pelajaran SMA-nya. What make it difference between your high school and this in the college is that in the high school you use a concentration. Itu kan ya? In the high school you use concentration, but here we use activity. This activity can be concentration if the reaction is in a liquid phase. Karena waktu karena kalau waktu SMA kan pasti contohnya reaksi-reaksi fase cair ya. So in the high school you use a concentration instead of the activity, because in the high school you've only learned about the liquid phase reaction. It is correct that the activity can be changed by a concentration if the reaction is in a liquid phase or in the aqueous phase. How if the reaction happens in the gas phase? How if the reaction happens in the gas phase? In the gas phase, the activity equals with fugacity. The activity for the gas phase, we use a fugacity. Gitu. Jadi in the liquid phase or in the aqueous phase, we use concentration as a activity, while in the gas phase we use a fugacity. Okay, in the thermodynamic, I think Pahadev already mentioned about the fugacity of the mixture. The fugacity of the mixture is the multiplication of its fugacity multiplied by its mole fraction. Yeah, it's a mole fraction and multiplied by fugacity of its pure condition. Okay. The problem is how we evaluate the fugacity. Yeah, how we evaluate the fugacity. The evaluation of fugacity is quite difficult. What we can evaluate is a fugacity coefficient. Fugacity coefficient is the comparison between the actual fugacity divided by a pressure, a pressure condition. Now we call it the coefficient, fugacity coefficient. Usually the notation is this. Yeah. Gitu. Now, how to evaluate the fugacity coefficient? You've learned about the equation of state. Yeah, in the thermodynamic, you've learned about the equation of state. You've learned about the van der Waals equation. You still remember? Van der Waals equation, Redlich-Kwong equation, Swaf-Redlich-Kwong equation, Peng-Robinson equation. Itu? I believe you've learned it, but I believe also you've forget all about it. Ya, karena saya juga sering lupa ya. Cukup wajar. Okay. Fugacity coefficient can be evaluated by those equation of state. Gitu. Okay. Yeah. So I think, yeah, but you can also evaluate the Fugacity coefficient by using this general approximation. By using this general approximation. Yeah, each subs gitu. You can evaluate the Fugacity coefficient by using this graph. Gitu ya. But you need to know the critical condition of each substance. Okay, you need the data of the critical condition, critical pressure and critical temperature. From the critical pressure and critical temperature, you will get a reduction pressure and reduction temperature. Gitu. PR, or reduction pressure, is P over PC, or actual pressure over the critical pressure. Reduction temperature is the actual temperature over critical temperature. When you have a PR and TR, you can evaluate this. You can find the PR, gitu ya, and then you can find the appropriate TR from this graph. The PR is the vertical line, and the TR is this the curvature line. Yeah, this curvature line. When you get the appropriate point, you have a PR and TR. You can evaluate the Fugacity coefficient by following the horizontal line. Itu ya, the horizontal line is the Fugacity coefficient. For example, gitu ya. For example, ini balik ini gimana ya? Nah, for example, if we have water or steam, yeah, or steam at a temperature of, let's say, 150 degrees Celsius and a pressure of let's say 2 bar to ATM. What is the Fugacity coefficient? Gitu ya. How to evaluate it? We need to know what we need to know at first. What we need to find out at first. What we need to find out at first?
Is it the critical thing, sir?
The critical condition, critical pressure and critical temperature of water. You can find it on the internet, or you can find it in the thermodynamic book. Okay, if I'm not mistaken, the PC of water is 221, about 221 atm, and the critical temperature is about 371, I think, degrees Celsius. Correct me if I'm wrong. Maybe you can search from the Google gitu ya. PC and TC. Okay. Is it correct? Yeah, you can search on Google, yeah, critical condition of water gitu. Its pressure and its temperature. Okay, once you have a critical condition, you need to find the PR and TR, the reduction temperature and reduction pressure. How about the PR? PR is P over PZ. So it will be 2 over 221. Can you please calculate it? And then the TC is T over, TR is T over TC. So it means that, remember, it needs to be converted to become Kelvin at first. Yeah. Could you please help me to calculate it? How's PR and how's TR?
The PR is 0.009.
0.009. And TR? How about the TR?
I think for the TR is 0.657, sir.
0.657.
657.
Okay, we need to find the PR at first. The PR is 0. PR 0. It's lower than this one. Okay lah, nggak apa-apa. Let's say it's around this gitu ya. It should be lower than this. It will be, I think the picture is limited. Or we can just change this to become 20 aja lah ya, biar ada mirip-mirip hasilnya. Okay, we change it to become 20 lah. Kalau 20 kan berarti 0.009 ya. Almost 0.1 ya. Oke, karena contoh itu aja. Oke, 0.1. The PR is here. When which one is the TR? TR is 0.657. This is the line of TR, the line of TR, gitu ya, yang curvature. This curvature is the line of TR. So it means that 0.657. It lies between these two, right? 0.657. 0.6. It will be near this line, right? The PR is 0.1. So we need to find the meeting point between this line and this line. It should be around this. It will be around this. So what's the value of Fugacity coefficient? Where's the value of Fugacity coefficient from this graph?
It's 0.4, sir.
Almost 0.5. Yeah, near 0.5. Let's say 0.3. Let's say from this we can get 0.39, for example, or 0.38. Yeah, it's gitu. That's how we evaluate the Fugacity coefficient by using this generalized model. Gitu ya? Bisa dipahami? Or is there any question? Okay. Bisa ya? Nah, kemudian after we get this Fugacity coefficient, what should we do? We need this. This is the chemical equilibrium, equilibrium constant, gitu ya, we just get from the previous equation, minus delta G equals to delta G equals to minus RT ln K. That K is goes here. Okay. The K equals to KY. KY is the constant for the fraction. KFP, or the coefficient of fugacity, gitu ya. The fugacity of each, the fugacity coefficient of each species powered by its coefficient stoichiometric. Gitu ya. Multiplied by delta pressure. Gitu. This is the explanation. This is the KY, gitu ya. KY is the mole fraction of each species powered by its stoichiometric coefficient. KFP, or coefficient of Fugacity coefficient, it can be calculated from each species of Fugacity coefficient powered by its stoichiometric coefficient, gitu ya, and the delta P, delta pressure. Gitu. Okay. For the ideal gas, Fugacity coefficient equals to 1, gitu ya. For ideal gas, Fugacity coefficient equals 1. Gitu. So that KFP equals 1 as well. Gitu. So for the ideal gas, we will have Ka equals to Kp. So it will be only be a partial pressure, yeah, partial pressure. Gitu. Okay. Okay. We will see. We will learn how to evaluate it later on the example. Yeah. Okay. That's the delta G. Yeah. So, if the delta G is less than minus 10, what will happen? If the delta G is less than minus 10, the reaction is
Is it very visible, sir?
yeah, it will be very visible. Yeah, it will be very visible. If it is in between minus 10 and 0, it will be quite visible. Yeah. How how if the delta G is positive? How if the delta G is positive?
It needs more
Need-
effort, sir. Sorry.
Yes. Okay. We need more effort, gitu ya. We need more effort to make the reaction happen, gitu. What kind of effort? One of the effort we can do is by changing the temperature. By changing the temperature, gitu. Okay. By it's just one of the effort, gitu ya. There banyak effort lain yang bisa dilakukan, tapi one of the effort is by changing the temperature. By changing the temperature, it's only one of the effort. Now the question now is how the temperature affect to the temperature. To the reaction. How the temperature will affect to the reaction. The temperature effect to the reaction depends on the enthalpy of the reaction. Gitu ya. The effect of the temperature determines by the enthalpy of the reaction. So you've learned that there are two kinds of, based on its enthalpy, there are two kinds of reaction. It is exothermic or endothermic. What is exothermic reaction? What is exothermic reaction? What is an exothermic reaction?
It's a reaction that gives out energy.
It's and that exothermic reaction is the reaction that generates energy while the reaction happen, gitu ya. It generates energy. And what is an endothermic reaction? What's endothermic reaction?
It consumes energy, sir.
Yes, it consumes energy. And for the for the exothermic reaction, the delta H is positive or negative? For the exothermic,
Negative, sir.
it is negative. And for the endothermic, the enthalpy is positive. Gitu ya. Okay. The effect of the enthalpy to the thermodynamic condition, to the thermodynamic coefficient, is expressed by this formula, or it's called Hof equation. From this equation, we can find the coefficient. We can find the effect of the enthalpy to the equilibrium constant. Gitu. Okay. So from here, we have d then k equals delta H over R times 1 T square do T. Gimana ya? If we integrate both sides, from the standard temperature, this is K standard, until T. So this is the KT. Gitu. If the delta H is not a function of temperature, what will happen? If the delta H is not a function of temperature, we can move the delta H over R to the outside of integral. Itu kan ya, kalau delta hanya tidak merupakan fungsi temperatur, kita bisa mengeluarkan dia dari integral, sehingga jadi tinggal seperti ini. Gitu. Okay, if we solve this integration, we will have this. Gitu. Nah, ini yang paling baik, nah ini yang paling sering digunakan untuk mengevaluasi konstanta kesetimbangan. This formula is commonly used to evaluate the coefficient equilibrium constant at a certain temperature. Gitu. Oke. Okay, any questions so far? If there's no question, we will try to use the formula to evaluate this. Okay, so now, what kind of data is needed if we want to evaluate the thermodynamic, if we want to evaluate the thermodynamic condition, the thermodynamic equilibrium? What kind of data?
Is it concentration, sir? No.
To find the first, first to find the Ka. What data we need?
The mole of the
Delta G. Itu kan ya?
I. Yeah.
Ini the delta G. Okay. For the fugacity condition, for the fugacity, mana tadi? For the fugacity, we need PC and TC. And for the, if the temperature is not the standard, we need also the data of delta H. So if we want to evaluate the equilibrium constant at a certain temperature, we need four thermodynamic data. Yeah, delta G, delta G, delta H, PC, and TC. Okay, now we want to evaluate this reaction. Yeah, so we need to find this for data for each species in the reaction. H2O, C2H4, C. So this is the reaction of the hydration of ethylene to form ethanol. Yeah, it's the hydration reaction from ethylene to form ethanol. Okay, we want to evaluate it at the condition of this temperature and this pressure. Gitu. Okay, so first we need to find the thermodynamic condition, thermodynamic data, delta G, delta H, PC, and TC. Gitu. Please help me to find this data from internet. Silahkan dicari datanya. Ada sudah dapat? Gimana? Bagaimana? Did you find it? Ada yang dapat nggak?
I found the Gibbs free energy and the enthalpy, sir, but not yet for the pressure and the temperature.
Okay, please mention what you've get.
For the water, is it in gas or in liquid form, sir?
Gas, the reaction in the gas phase.
For the gas, the enthalpy is negative 228,572.
200,
28,
28,
572.
572. Okay,
Oh, sorry, sir. That one is for the
enthalpy.
Oh yeah. No, Gibbs free. Sorry. Yes, that's correct.
That's correct, yeah.
Yes.
Minus 228,572. Okay.
Yes. And for the enthalpy, it's negative 241,818.
Negative
241,818.
241,818. Okay. How about the ethylene?
Ethylene, for the Gibbs free energy, it's 68,460.
Minus or
Positive, sir.
positive? Okay. 68,
460.
460. Okay. How about the enthalpy?
52,510.
52510. How about the ethanol?
Ethanol, well, hold on, sir. I'm not sure about this one since, if I'm not mistaken, before in the thermodynamics class last semester, it was different between C2H6O and C2H5OH.
Oh, really?
Yes.
Is it different in the phase or?
I'm not sure, sir.
Yeah, just mention what you get. Okay, which occurs, okay.
For C2H6O, for the gas phase, the Gibbs free energy is negative 168
Negative
490. 168 490.
168
490.
490. Okay.
And for the enthalpy, it's negative 235 100.
Okay. Okay, how about the PC and TC? How about another? How about the other?
I found the critical condition, sir.
Okay. Okay. How about
For water, the critical pressure is 217 atm.
okay.
For the critical temperature, it's 647.
647 Kelvin, yeah.
And for ethylene, it's 50 atm
Okay.
and 282 Kelvin.
82 Kelvin. Okay.
For ethanol, it's 63 atm and 513 Kelvin.
Okay. Okay. What we do next is evaluate the delta G and delta H of the reaction. So delta GR. So the delta GR equals with the coefficient of the coefficient times delta G component. So what's the coefficient of water? Berapa koefisien air? The stoichiometric coefficient? Here. What's the
Oh, is it all one, sir?
positive or negative?
For the C2H5O5, OH is negative, positive, but the left is negative.
Okay, it's just -1, -1, +1. Yeah. So then now you can calculate the delta GR and delta HR. Okay. Berapa? Ada sudah menghitung? Oh, ternyata ini ada. But the data quite different because the unit is different. Tapi nggak masalah. Oke. Oke ya.
Uh,
Ya.
for the Gibbs free,
Hmm?
it's minus 8,000.
Minus 8,000.
378.
78. Again, delta H. Delta H.
Minus 44,792.
Okay. Okay, yeah. Now you have a delta G and delta H for the reaction. What you need to evaluate at first is the first, from the delta G, you need to evaluate the K. I write it as a K298 or standard K. Yeah. Now you have delta G. You can calculate this, or in another form, you can calculate by using K298 equals exponential minus delta G over RT. And this T is how much? What is the T here? This one is 298 because this one is the standard one. Okay. After evaluating this K298, next step, what you need to do is wait, okay, yeah. What you need to do is evaluate the next K this. Okay, the algorithm is like this. Why I need to the algorithm is first calculate K298 from the following formula. K298 equals exponential minus delta G over RT. Okay, in the T here, of course, 298 Kelvin. And then number 2, calculate K at a certain temperature. Here, KT from the equation. From which equation? By using the Hof equation. Ln KT over K298 equals tadi apa? This minus delta H R over R 1 over T minus 1 over 298. Yeah. Then calculate, not calculate. determine P ya, PE. Okay. So calculate PR, P over PC, and TR, T over TC. From here, you can get phi from graph. Okay. Okay, then now okay, use the formula KT equals KY times KP P over delta P. Gitu. KT you can get from here. Yeah. KY you can get from sorry. Okay. KY and K this one. So it will be because the reaction is this. Let's say this one is A, this one is B, and this one is C. So it will be YC. The coefficient is 1 gitu ya. Jadinya YC just YA, YB. Ya. Terus AP is PC over PA, PP. Gitu. Gitu. So by solving this equation, you will get this. And this one is the mole fraction at the equilibrium condition. Gitu. Okay, I want you to try to calculate this. Gitu ya. As far as you can. You can calculate this as far as you can, and we will continue. I will continue later to explain how to finish it. Gitu ya. Please calculate first ya. Berapa? How's the K298? How's KT? And how's Fugacity coefficient for each species? Gitu. Dicoba dulu dihitung ya masing-masing. Nanti besok kita lanjutkan. Okay, any question? Any question? No?
Sir, will the PowerPoint be uploaded to the EduNext or no, sir?
Yeah, I will upload it at first in the MS Teams, and later I will upload in the EduNext.
Okay, sir. Thank you.
Okay. I already opened the presence. Kalian udah absen belum?
Udah, sir.
Udah ya. Okay. I already opened the attendance list on the CX. If the absen, bentar. I'll check. Oke, ada yang belum absen, silakan yang belum absen. Oke. Okay, yeah. Please try to calculate at first for the K298, KT, and the Fugacity coefficient. Itu. We will continue to discuss. We will continue to finish the calculation tomorrow. So, if there's no more question, I will today's session is dismissed. See you again tomorrow.
Thank you, sir.
Thank
Thank
you
you.
very much, sir.
Thank you, sir.
Okay.
Thank you, sir.